last time we started looking at the stability of the spanning tree polynomial, and we ended with this following lemma, which said that if A1 to AN are symmetric PST matrices and S is just some symmetric matrix, then this polynomial, which is the determinant of the summation of xi, so it's a polynomial with the xi's, so it's xi times ai, and this is summed from I going from 1 to n, and this polynomial is real stable. So as long as the AIs are PST and and S is symmetric, okay. And for this, I mean, just to keep in mind that the convention that you have been following is a zero polynomial. So there's a situation where all the A's are zero, that is covered, and we just assume that the zero polynomial is considered stable in this set. Okay, so so now we want to prove this lemma. So any questions about the lemma? Okay, so why is this lemma important? So yes, why is this lemma important? So let's look at this. So this is because of the so-called matrix tree theorem, to Pershoff, it's old result. So suppose you're given some graph G and fix some vertex R in G. So you fixed a vertex R in G, and now you arbitrarily assign some direction to each edge. This doesn't really matter. This is just for definiteness. We just assign some direction to each edge in an arbitrary fashion. So the graph just has some arbitrary direction. And now what you do is you define these these edge vectors, which are now n-1 dimensional. N is the number of vertices in G. And what is this n-1 dimensional vector? So you have so whenever you have a edge which is none of the two vertices are these chosen root vertex, then you just put it as EV minus EW. So this is a vector, n-1 dimensional vector. The entry corresponding to V is 1. The entry corresponding to W is -1. And all the other entries are 0. And if one of them is the root, then you just put a 1 at the non-root vertex that is in the edge. Okay, so that's the definition of an edge vector. Okay, so you've just chosen one arbitrary vector, you assign some arbitrary directions, and then you decide. You basically for each edge you have made a vector which has two entries, 1 and 1 minus 1. When the edge is not incident on the root vertex, and it has exactly one entry, which is just 1 when the edge is incident on the chosen root vertex. Okay. So then what does the matrix tree theorem say? So
sorry, Piyush.
Yeah.
Sorry. Yeah. Can you just yeah.
So this is for each edge you have a vector which is n-1 dimensional. If the edge is not incident on this chosen root vertex, then it is just the usual. So you have a 1 at one location and a -1 at the other location. Where you put 1, where you might put -1 doesn't really matter. But just choose some convention for each edge separately. This is the direction.
Right.
And then if the edge is incident on the root vertex, then you just put a 1 at the non-root.
So in the last line, you are actually assuming every self group is there, right?
Sorry.
So when V equals to W, so that means you are assuming
there is sorry. This is just draw. This is not incorrectly. So when what I mean is when W equals to R.
Oh. So that was my Okay. Yeah.
Okay.
Yeah.
So yeah. Okay. So now. So then the spanning tree polynomial. So recall what the spanning tree polynomial was. You go over all this. So you have one variable per edge in the graph. Every edge has its own variable, distinct variable. And then you go over the spanning trees in the graph. And for each spanning tree, you have a monomial. And the monomial is the product of the variables of the edges that are in the tree. Right. So that's the spanning tree polynomial that we have seen. And the matrix tree theorem says that this. The matrix tree theorem says that this has this nice representation that the spanning tree polynomial is exactly a determinant of the following matrix. What is a matrix? So you look at these rank 1 matrices, which are chi-e transpose. For each edge you have this chi-e transpose matrix, and then you multiply that matrix by YE. Okay. How many entries does this chi-E transpose matrix have? How many non-zero entries does it have? So how many non-zero entries does chi-E have?
Chi-E is for each edge, right? So
Yes.
it has one non-zero entry or?
Yeah, 1 or 2, right? So if it is incident on the root, then 1, and if it's not incident on the root, then 2.
If it's not incident on the root, why is it 2? Because it's EV minus EW. Oh,
yes, it has 2 non-zero entries.
Yeah. Okay.
So what does this chi-E transpose look like? So if it is a usual edge, which is not incident on the root, basically it looks like a +1 on the VV entry, a +1 on the WW entry, and a -1 on the VW and WV entries. That's exactly what this chi-E transpose looks like. If it is actually on the root, then it is just one diagonal entry at the non-root vertex. Right? So these are very simple matrices, and then you multiply them by y. They are rank one matrices. You multiply them by and sum them all across all the edges and take the determinant. This is the span tree one.
This E is undirected or directed.
But it doesn't matter, right? So as I said, how it matters. So I said that I arbitrarily assign a direction, and what was the direction doing? It was just assigning a sign to this chi-E, right? And no matter what sign you do, this matrix chi-E transport does not depend upon that. Right? So if I multiply chi-E by -1, this matrix does not change.
Oh, okay.
Right? So this direction doesn't. So this direction was just you can forget about the direction if you want. I mean, the only thing is that somehow you have to, for each edge, you have to decide where to put a +1, where to put a -1. That's all about the direction. Otherwise, the direction doesn't matter at all. There's no.
But Piyush.
Yeah.
But chi transpose.
Yes.
When E is when chi-E has 2 entries, that means when VW are not incident on the special vertex R, right?
Yeah.
So chi transpose will have 4 non-zero entries. Some of them will be +1, some of them will be -1. Right?
Exactly. So let's see which ones are +1. So as I said earlier, so the +1 entries are on the diagonal, the VV entry and the WW entry. Correct. And the -1 entries are the off diagonal, the VW entry and the WV entry.
Oh, so that is why the direction doesn't matter. Okay. Yeah. And
so this is exactly, there's a graph Laplacian, by the way, right? I mean, I did not mention the word. This is exactly the graph Laplacian. Right. Except that I have, it's like, so basically what it is a minor of the graph Laplacian. If you think about it, you have taken the root vertex and removed the edge and the column corresponding to it.
Right. So
that's what this
is. And YE is the edge weight.
Yeah. And YE is the edge weight. Yeah.
Y is an edge variable, right?
Yeah, edge variable, which, so if you put a real number, it just becomes edge, which is just the weighted graph population.
Yeah, but currently we are looking at a symbolic matrix.
Yes, currently we are looking at a symbolic matrix. Yeah, so this is true. This is a symbolic identity. Yeah. Okay, so this is a minor of the weighted Laplacian. Okay, so let me just okay, so what next? Yeah. So note that if now given this theorem, the Matrixy theorem, the real stability of tau g follows immediately, right? Because why? Why is that?
The previous theorem.
Yeah, because chi transpose are PSD matrices, right? By definition.
So here, this matrix is basically saying M u comma v is minus y, and the diagonal element is the summation of y's of all edges incident to.
Yeah, exactly. So that is exactly the graph Laplacian, except that the row and the column corresponding to the vertex R are gone. So it's a minor of the graph Laplacian. Is n-1 cross n-1 minor of the graph Laplacian. So in particular, this also means that all the minors of the graph Laplacian are the same determinant, right? Which is equal to the. Okay.
All minors minus the root. Okay, no, root can be anything.
Yeah. So okay. So let's do the proof of this. By the way, so this everyone see, right? So given this theorem and the previous lemma that we had last time, the real stability of tau g follows immediately, because now you have expressed tau g as a determinant of linear sum over variables of PSD matrices. Chi transpose, yeah, by definition is PSD. It's symmetric, and you take inner product with any vector. It's a perfect square, so it's non-negative. Okay, so now let's try to prove this. So what is this? What is this chi e? So it's easier to think of all of this in terms of the edge incidence matrix. So it will help a little bit. Same thing, just a different way of writing this. So what is this edge incidence matrix? So you now just stack these columns, okay, one after the other. So it's a n-1 cross m matrix, where so m is the number of edges. Okay, where the column correspond to the edge E is just chi. Okay, so here's an example. So I take this graph G 1, 2, 3. This is, I assume that this is the directioning also. So like you go from the smaller to the larger one, and I put 1 as the root. So then what is this? What is my this edge incidence matrix? In this case, it's a 2 cross 3 matrix, right? And the edge 2, 3 gets a 1 minus 1. The edge 1, 2 gets a 1, 0. And the edge 1, 3 gets a 0, 1. Okay, and so each column is, by the way, yeah, so this is again to just highlight that each column is only determined up to a sign. So I can just arbitrarily change the sign of each column independently. Okay, so it changes the matrix.
I'm hearing some music from somewhere. Is it
music?
Huh?
And then putting wins on the board.
Oh, is it?
Yeah, I am also hearing it now, but not anymore. Not anymore. Yeah. Is it you know?
Yeah, it's gone now. It
Okay.
was there earlier.
Yeah, it was. I was the culprit. Sorry about that.
Okay, so yeah, so each column is only determined up to this sign. So yes, I can arbitrarily change the signs. Of course, the matrix changes, but what doesn't change is this matrix for which you want to take a determinant. So what is that? So it's that. So then observation.
So sorry, Piyush, what did you say is not determined up to a sign? I'm sorry.
So what I'm saying is that so I mean I can arbitrarily change signs of each column. It wouldn't matter for what I'm going to do next.
Okay.
Yeah. So the observation is that this whole this summation y chi transpose is exactly this edge incidence matrix, so which I'm calling xg, times the diagonal matrix which has these y's times chi g transpose. So this is a standard way of writing sums of rank 1 matrices, and it's also easy to see from both any of these two descriptions that so let's just write on the dimensions just to make sure that we are doing it fine. So this is n-1 cross m. This is m cross n, but it's a diagonal matrix, and this is m cross n-1. That's the transpose. Okay, so now what? So now we will use something called the Cauchy-Binet.
The diagonal thing will be m cross m, right?
Yeah, m cross m. Yeah. Right. So now we use something called the Cauchy-Binet formula, which is again something that is easy to prove once you have seen what it is, which says the following, that let A be n cross S cross T and T cross S. So then determinant of AB, right, which is the S cross S matrix, right, is given by sum over all subsets of 1 to T of the determinant of A, where you only take the subsets corresponding to, oh, maybe S is not a good thing here, so let me call something else. So you take S, so you take all the rows, but you only take the and these things are of size, all subsets of T of size exactly S of and W. Okay, so you take the columns corresponding to W in order, and you take all the rows of it times the determinant of the corresponding. Now B is T cross S, so now you take the corresponding rows of B and all the columns. Okay, so let's prove this later. Right now, let's assume this and see what this tells us. Okay. So is the statement clear? So in particular, this automatically tells you that if yeah, so I mean,
can
in particular,
notation?
Sorry,
can you repeat the notation of AS?
Yeah, so this is just saying that you're taking all the rows and you're taking the columns corresponding to W. So when I put so this is like just taking the submatrix of A, where the rows are the set 1 to S, which is all the rows, and the columns are the set W. So it's a S cross S matrix again, right? Is that clear?
Yeah. Okay.
Okay, so this is also symbolic identity, okay, and it can be proved symbolically. So it's just by the definition of the term. So, okay, so okay, so now let's see what this means for us, right? Okay, so okay, so what does this tell us in our setting? So we had the summation ye chi e transpose e in e, which we proved is equal to the summation. Well, is equal to this xg, and let me call this dy, the diagonal matrix of y, times chi g transpose. Now, what is this diagonal matrix of y? So it is just multiplying the corresponding columns, right? So let me just say so this is like so this just multiplies the column. So this thing. So the columns are exactly ye times chi. That's exactly the columns of this guy. And the rows of this the rows are exactly chi transpose. Okay, so now let's apply Cauchy-Binet to this. So then this that so let me okay. So what is this? What does the Cauchy-Binet formula give us? So it says we have to go over all subsets of M. Okay, so all subsets of edges. But what is the size of the subset?
n-1.
Yeah, n-1. So if you take n-1 subsets, size subsets, and then what do we have to do? So we have to take a determinant of this matrix. So we have to take, what are we going to do? So we're going to take this, so these S columns and take the determinant. So if I take S columns, in particular the YEs, because they're just multiplying columns, they just come out, right? So I can just write it like this. So this is part is just there. And then what do I have? Then I have this determinant of XG, which is XGS, which I just let me call, which is just you just take the columns of S. Just takes the column corresponding to S. And what is the other thing? That's also the same thing actually, right? Because you're just, so it's just a transpose and now you're taking rows. So it's a determinant of the matrix XG. So what it really being very correct, it is exactly this. So the transpose of that. So this whole thing is summation of S subset of M, where size of S is n minus 1. E in S. And what is this here is determinant of XGS square, where XGS is the matrix obtained by choosing columns of XG for exactly those for E corresponding to E to those edges that are in the set S. Right? Okay. So let's just write this thing again. So what we have shown is this determinant of summation YE chi E transpose is equal to the summation over all subsets. All subsets S of the edge set of G, which have exactly n minus 1 entries. For each of those things, I get to multiply the variable corresponding to that edge, and the corresponding coefficient is the determinant of XG. Yes. So now, if S is a subset of EG of size n minus 1, what is this determinant of XG? Okay. Okay.
Want someone say that if S is not a spanning tree, something is repeated, and so it will be 0, right?
Yeah. So no. So the issue is that if X is not a spanning tree, there will be a cycle.
There will be a cycle, right?
And that will give you a linear dependency, and the determinant will be 0.
Right.
If it is a spanning tree, it has to be +1 or -1.
Right, right.
That's the point. So let's just check that.
Right, because -1.
So because you have n minus 1
Correct.
things, if it is not a spanning tree, there must be a cycle.
Correct. Yeah.
For this proof, we could have also assumed G is Kn, right? And then later just substituted Y is to be 0.
Yeah, nothing. Yeah, really. So the only thing that the only thing that you are going to do here is that, so the only sort of thing that depends upon spanning tree is just this fact that if you take the edge incident matrix of a spanning tree, edge incidence matrix of a graph which has n minus 1 vertices and n minus 1 edges, then it has to be 0 if it is not a tree, because then it will contain a cycle. And so now,
This was
So the sum of the cycles is 0.
no, because the whole point is that you take any cycle, then this XGS is a matrix which is not full rank, so its determinant has to be 0.
Yes. So sum of the rows corresponding to a cycle will be 0.
Well, yeah, you have to be careful about the signs. So basically, you have to take each column multiplied with the appropriate signs. So you take a cycle, put the vertices of the cycle in some order, and now you just and now you just make sure each column you have the higher guy in one, +1, and the lower guy -1. Sum it over, and let's see. Okay, so smooth. So these are now basic facts that if so consider, so if this graph, if the edge subgraph of G given by S as the size of set is equal to the size is not a spanning tree, then it must contain a cycle. But then there is a linear dependence between the columns and the columns. So a non-trivial linear dependence of the XGS, so that the determinant of this X with okay, so this gives one thing, and the other observation is that if xg, if the edge subgraph given by S is actually a tree, so it has to be then a spanning tree, because, then the determinant of X is actually ±1. Why is this?
So for every non-root edge, you are choosing one of the edges, and so and one edge can be chosen by exactly one vertex. So you are basically orienting the edges.
Yes, but that
and there is only one way to orient them.
No, yeah, but that is fine. But how do I still like to argue? So the easiest way to do this is to just say that any spanning tree, because the tree has to have two leaves, and one of them must not be the root vertex. So you start at this non-vertex root, right? And then that means that vertex has exactly one edge incident on it. So if you just take the row corresponding to that vertex, it is exactly 1, 1 or -1. So you take that out, and you now go to a minor, which is a smaller spanning tree on a smaller set of vertices, which contains the root vertices, and you keep going on until the last thing where you are left with just the root, or the root plus one vertex, in which case it will just be a 1 cross 1 matrix with a single 1 or -1. So you every time you're just multiplying by 1 or -1, and you're expanding along a row which has exactly one non-zero entry. So you just get a +1 or -1. Okay. So this is, and this is the proof. So basically only the spanning trees could survive, and the spanning trees do survive with coefficient 1. So this proves the theorem. Okay. So now we have that the spanning tree is real stable, and therefore the edges have this negative dependence. In fact, we have also seen enough to prove why they have.
What did you say last? Because there's
negative dependence, right? So probability of E in this random spanning tree.
Oh, okay.
The thing that we saw. Okay. So this negative dependence can be generalized to something called negative association, like not just single edges, but disjoint sets of edges will also have that, and that can be done more or less abstractly. Just the fact. So basically, for any sort of similar real stable homogeneous polynomial generating function distribution. So the distribution which has such a span tree like real stable generating function will have, if it has, because then it will also have by the same argument negative dependence, and almost abstractly from that you can also get negative correlation. The point is negative association. The point is that conditioning, like if I take the span tree distribution, the uniform distribution of span tree, and condition on an edge being present in the span tree. So I look at the span tree distribution, condition on my favorite edge being presented. Does that distribution also have negative dependence between edges?
So you are plugging y equals to 1.
Yes, exactly. So the polynomial still remains real stable. The whole argument we did for the span tree polynomial, it still goes through. And so even after conditioning on an arbitrary set of edges, it still remains real stable and still has its negative dependence. So you can use this to show that that arbitrary subsets of edges also have negative dependence, which is called negative association. Okay, so that we'll maybe I'll do it in a homework or something.
Sorry, Piyush. Did we? I'm a bit. I don't recall.
Yeah,
Did we do the fact that? So you're using some fact about real stable polynomials, right? So
yeah. So what is the fact that you're using? So
what can we prove that the spanning tree polynomial is a real stable polynomial?
Exactly. So so the point is that real stability is preserved under conditioning. Why? Because what is conditioning?
That I got it.
Because it's just setting y to 1, right? Which we saw.
I got that. I'm saying that what are you using about this real stable polynomial to conclude negative correlation?
Oh, that we did, right? So we did this proof that so the same proof that we did for span tree polynomial will work for any homogeneous real stable polynomial. Remember the proof that we did last time? So we took this so to prove that the edge E and edge V are negatively correlated. We just looked at the polynomial when all the other variables are set to 1, and we took 1 plus U, 1 plus V.
Right.
And then this polynomial is also real stable, and from real stability we got negative dependence. Okay, so actually this idea that if you have a probability set of probability distributions which are closed under conditioning in this way, and which then they have then negative dependence applies negative association, is actually quite old. It goes back to Feder and Mihail, and they were not talking of real stability. Just real stability makes implementing that idea much easier. So it's a famous paper called Balanced Matrix, where this idea is there. Okay, so next let's go to so next let's try to do something so completely different. So we have looked at, so far we've looked at this perfect matchings, we have looked at spanning trees. Now let's look at arbitrary matchings and prove something, give a different proof of a theorem of Heilman and Leib on the roots of the matching problem. Okay. So
sorry again to interrupt you. So what have we said about perfect matching other than the permanent?
Yeah, that's all. So this is just the third example. Basically, that's all. So now let's look at something called the matching polynomial. So this is just this will involve a slightly different way of proving. So we have I just want to say, like, what are the different ways of proving real rootedness. So for the first one, we sort of the first example, we had some very obvious kind of things, right? Like we started with the linear polynomials, then we multiplied, and then we kept doing operations. And yeah, that was it. And we'll do a similar thing here, but the operation that we will do will be maybe slightly more non-trivial than the previous ones that we have been doing. And we'll get this. So that's the point of this example.
The goal is to prove that this is real stable.
Yeah, but yeah, so we'll see what the matching polynomial is first, and then. Okay, so what is the matching polynomial? So the obvious way of defining it would be something like this, that so is would be that you have a so put a variable ye on every edge. Okay, and then define mu and y. And this defined it to be the your sum over all. So matching is a collection of edges, no two of which share a vertex. So everyone knows what a matching is, right? Okay. So not perfect, it's arbitrary. So just any collection of edges, no two of which share a vertex. That's it. And then what I will do is just do this. So the first question I ask is this real stable? Okay. So let's check some examples. So let's take a single edge. What is the matching polynomial for a single edge?
Y.
No, right? It is 1 plus 5.
Y1.
But there's an empty matching.
Okay, empty matching.
Yeah. So this is real stable, but maybe this is misleading. So let's look at something else. Let's look at two things. And again, yeah. Again, real stable. But what about 3?
Y1 plus Y2 plus Y plus Y1 Y3.
Yeah. Is this real stable? So I'll leave you to check that is it done or that it's not. I hope I'm not making a mistake. But yeah, in general, the matching polynomial is not real stable. But something else is. So, and we'll tell you that this mu g is actually stable in a certain way, which is that if I now put a, so let me call this actually mu hat, and the usual matching polynomial, this is why it's defined in this weird way, is you just put some signs.
One thing actually before, so the matching polynomial and independence polynomials are quite bit same, right?
Well, the matching polynomial is sort of like the independence polynomial of the so-called line graph. Yes, it's a special case of the independence polynomial. Because what you're doing is basically you're thinking of a graph in which the vertices are not the edges, and two vertices are adjacent if the two edges share a vertex, and a matching is exactly an independent set in that graph. But these graphs are very special. So line graphs, not every graph is a line graph. So such graphs that you obtain, you take a graph and when you make the edges as vertices and then put a adjacency between two edges if they share a vertex, it's called a line graph of a graph. The graphs that can be generated by line graphs are a very special class. So in particular, they cannot have these so-called claws. They can't have induced subgraphs that look like this. So they're claw free. Okay. So yeah, but so the usual matching polynomial is defined like this. Okay, I will actually do something. Maybe I messed up something. Let me just come back to it. I'll actually have a variable per vertex. Yeah, okay. Yeah, so I'll do this. I have a variable per vertex now. And I will again go over all matchings. And for each matching, I will have a term that is like -1 to the power the size of the matching. And the product over all the vertices says that V is matched in so this is called the matching polynomial. And we'll prove that this is a real state. So some history. So so they usually Heilmann Lee. So this goes back to Heilmann and Lee, who studied who were especially focused on the case when all these variables are actually equal. Okay. Just in case. All x are equal. Actually, yeah, so this I shouldn't call the matching polynomial. So let me again call it something else. Like so this is some polynomial to matching, which is real state. So they were interested in the case where this is interested in the case where all x are equal, and then they
what do you mean x are equal?
So you just you make it univariate. So just set all x equal to x. So it's a univariate polynomial. But then they did a lot. So so they actually showed that yeah. So then they showed. So in this formulation, yeah. So in this formulation, they showed that the roots will lie on the negative. I think negative. Yes, no. So that's fine. So the roots. So they even showed bounds on the roots. So where in terms of the degree of the graph. So also proved bounds on the location, like on the value of the roots, values of the roots in terms of the degree of the graph. So notice that if you prove it is real stable, then in the univariate thing it has to be real rooted, right? And so then you know where the roots have to be on this line. The graph. The proof I will do, I don't know who it is due to. The first time I saw it was in a lecture by, it was in a talk by Nikhil Srivastava. It's different from the Heilmann-Lee proof because they used a technique called interlacing, which we will also see, and which is also very powerful. So interlacing those two. The proof I will do will be based on so as I said, so we will do a proof based on which does not immediately give which is maybe simpler, but it does not immediately give the extra information that Heilmann-Lee got about locations based on closure properties. So I made yeah, so remember seeing it in a talk.
I have a couple of questions. The first is that I mean, we can always think of some recurrence for these polynomials by deleting edges and
exactly. So that's what. So that's what Heilmann-Lee did. So they take the usual edge deletion, edge contraction recurrence, edge deletion, and edge deletion and edge addition. So yeah, so some recurrence like this. So which one?
So yeah, I was going to ask.
And basically they showed that the root, so these are basically you're getting matching polynomials of smaller graphs, the bigger graph in terms of the smaller graph, and they show that these polynomials interlace, the roots interlace. So
Oh, so there is a general understanding of what kind of recurrences will preserve real stability.
There's no general such thing in that sense, but yeah, but if you can prove interlacing, yes, because then you're just showing that there are all the roots are there on the line. So then you're fine.
Okay, and the other thing was, what is the meaning of negative co-association in for the matching polynomial?
Yes, so now, so in this case it won't make. So in this case, all those probabilistic notion go out of the window because now you have negative things, right? So now we will not have that, but we'll still get something out of it, which will be very like some probabilistic thing out of it, which will be interesting. So yeah.
Okay.
So we'll see what is a corollary of this being real stable. A nice commutator corollary, which is otherwise quite hard to do. Well, yeah, otherwise quite non-trivial to do. Okay. So okay. So let's do a thing. So let's start again with a polynomial. But maybe before the polynomial, let me say what is this closure property that we're going to use. So we'll use this something called the multi-affine part. What is multi-affine part? So let me first take a very trivial kind of thing. So suppose that fx equals so motivation. So suppose I take a univariate polynomial. Okay. Okay. Right. Which has real coefficients and is real. Okay, and assume that that let's say a1 like a0 a1 are not zero. So my claim is that then, so there's some very trivial thing that this polynomial a1x plus a0 is also real root. And this is sort of trivial, right? I mean that if I assume real coefficient, it is trivial.
Isn't every linear polynomial rooted?
Yeah, exactly. So let me drop this real coefficient thing. Okay, so I just say that which is real. Somehow. So I somehow have managed to construct some polynomial which is real rooted, possibly with non-real coefficients. I don't know if such a thing even exists, but like yeah. Okay. So we take this, and then this is real. And why is that? This is easy because how will we?
So it factors into product of quadratics and.
No, it's something even simpler. So if it is real rooted, then a0 is like the product of the root sort of, I mean, up to a factor. Yes, a1 is like something else, and you take the ratio that is also something of real numbers. So what is this? What is exactly this? So the point is that this a0 is exactly f0, a1 is exactly f prime 0, and so the point is that this so a1x plus a0 is equal to 0 if and only if x is equal to minus a0 by a1, which is just minus 1 over f prime 0 over f0. But f prime over f0 we have seen several times is easily implementable as a, but the point is that this, what is this f prime 0 over f0? It's exactly summation minus 1 over ri, right? Ri is the roots of. So this is the usual, just directly from factorization. You have this, right? So, but then this is real. This whole thing is real, and so this is also real, and so. So maybe let me do something else. So real rootedness maybe is too strong. Maybe something else. So which has no roots in the upper half plane, which might happen if it is not real rooted. So if it is not, does not have real coefficient, which is no roots in the upper half plane.
that implies it is real rooted, right?
Well, only when the questions are real.
Oh,
now I'm not assuming all of that, right? So then A also has no roots.
so upper half plane, you mean imaginary part strictly greater than 0? Or?
Yeah, strictly. So open upper half plane. Okay, and why is that? Again, just take this. So
Each of these imaginary parts is strictly negative.
Yeah, so let's just look at it. So because so what is this root? This root must look like minus a0 by a1, which is exactly minus 1 over summation f prime 0 by f0, which is 1 over summation I going from 1 to 1 over ri. Now each of these ri's, it has imaginary part that is okay, let me just say not open but closed. So all the roots are actually in the open. Okay, so each but by assumption, this ri must be strictly less than 0, right? Because there are no roots in the upper half plane, closed upper half plane, and so imaginary part of 1 over ri should be
Greater than 0.
Yeah, greater than 0. So this whole thing implies the imaginary part of x. Okay. So what does this say? So this says that if I take the so-called multi-affine, if I take the affine part of f, so if f is a polynomial that has no roots in the closed upper half plane, and I take the affine part of f, that also has this property. What is the affine part? Just the constant, like the part which is degree at most 1. Okay, so is that clear?
So
this we have,
this doesn't work for the if you took the quadratic part or something, it fails.
Yeah, the quadratic part in general would fail, right? So because now I don't have this yeah, so quadratic part I think will fail. Yeah, so
okay. No, I was not seeing how to extend it, so I was just
So it's I think it will fail. I haven't tried, but I'll be surprised if it works. Yeah, there might be, you might be able to get some properties that under certain conditions the quadratic part also works, and so that's interesting. Okay, but but this one just works in general. So the only thing we assume is a0, a1 non-negative, non-zero, and we assume that there are no roots in the closed upper half plane. That's it. Okay. Cool. Okay. So in fact, if you assume
but if you assume that this is real rooted, then the top two parts also you will be able to get this way, right? Because just by substituting by 1 over x or something.
Yeah. So wait.
That's interesting. So the top two part will also be real rooted.
Yeah, because of I think it will just follow because you have this Newton's inequalities. Yeah. So quadratic will also work. Yeah, because the last three things will also have they will satisfy the
So okay.
Yeah. Okay, so so that's good. So now, so okay, so we did it for the univariate case, but the same thing more or less applies as it is in the multivariate case also. So let's just do that. So let p x1 up till xn.
But Piyush, it will stop at quadratic, right? You try for cubic, having Newton's inequality won't mean much.
Yeah. So Newton's inequalities doesn't imply real goodness. So even for real goodness, this argument certainly stops there.
Yeah.
So let p x1 to xn be real stable, and let me just have this thing where I write it, I expand it in degrees of xn. Okay. So summation x to the I x to xn I goes from some 0 to t. Okay. Then
No, what is AI? Sorry, please. What is this AI?
so I mean I'm just such that I mean I'm just expanding this p and powers of x.
Okay. Sorry.
Yeah. So AI is exactly the coefficient of x1 to the power I. Yeah. Okay. So now so then the polynomial q x1 xn, which is just taking the multi-affine part of with respect to x1, which is what? Which is just x1 times a1 x2 to xn plus a2 x2 xn
Plus A0, right?
Yeah. Is also realistic. Okay. So let's prove this. Okay, so suppose not, right? So then so if okay, so if somehow a0 and a1 are both identically 0 or something, then we are done, right? Because q is then identically 0, and our assumption in our convention I like 0 polynomial is also is taken to this table. So a0 a1 are, we can assume, are not identically 0. Okay, good. So suppose that q is not realistic. So suppose q is not realistic.
Sorry, why can we assume A1 and A0 are not identically 0?
Well, because I mean, it's for trivial reason, because if they were identically 0, then so is q, and our convention is that the 0 polynomial is taken to be realistic.
Okay.
So suppose q is not realistic. Okay. So then what does it mean? Then there must exist.
I didn't get the case when A1 is 0, you are still left with A0.
No, I'm saying if both are non-zero, so that is the one.
Oh, okay.
Both are 0, then
so
both
one
are
of them. Okay.
Yeah. So then okay. So suppose it's not realistic. Okay. So we want to just argue that that is not possible. Okay. So well, okay, and it must. Wait, just one second. Yeah, okay, so let's handle the yeah. So suppose it's not realistic. So then there exists x1 to xn, all having positive imaginary parts. Says that q of x1 to xn is equal to c. So now the claim is so. So first thing is okay. So let's ignore this identically 0 part for now. So let's just look at this the interesting part. So suppose so this is 0. Good. So now first thing is can a0 of x2 to xn be equal to 0?
A0, because A0 is substituting 0 in place
So
of
assume
x1, so it is real.
right now assume that a is not identically 0. A0 is not identically 0.
A0 is real stable because
Yeah, exactly. So this cannot happen because it cannot happen because A0 is also real stable. Okay. Why is it real stable?
Substituting 0 in place of x1.
Yeah,
By
exactly.
Horowitz theorem.
Yeah. Yeah, that's not. Yeah, that's well before closure. But yeah. So that's the closure properties we saw by substituting. Okay. Now.
So now you
And
just
can
have
what
a
about
univariate
can?
counterexample.
Sorry.
It's now you already have a univariate counterexample, right? Which is you have
So I just have to argue something about A1 also, and then we are done. We assume that A1 is not equal to 0 also.
A1 is applied by getting a derivative under differentiation, real stability is preserved. So,
yeah. So cannot happen. A2 is obtained by looking at this D del x1, P x1 to x1. So to see. Assuming that this is also. Okay, so these are so these two cannot happen. So assuming of course that both are this. So then then our univariate thing already does. So then except for this thing that you have to worry about this.
Why
so
does
we assume this closed.
Why does the univariate thing not do? Because you get x1 times something which is not.
Yeah, so the only thing is that I assume closed upper half plane. I want to do up. Yeah. So, but it's the same. Yeah, it's the same. That's not a problem. I mean, the whole thing is that yeah. So this thing is actually like yeah. So if I put x2 to xn in the upper half plane, so this univariate polynomial that I'm getting, right? So this univariate polynomial. So no. That this polynomial Rx1, which is just given by P x1. Well, sorry, I have used a value. So then there exists. So Rx, Px, has no roots in the closed upper half plane. Right, because otherwise this if it had, then the polynomial obtained by putting the root in the first coordinate will be real stable, but that is contradicting this. Okay. So we have the so then the univariate. So,
sorry, Piyush, what did you assume? I got a bit confused. What did you assume? Can you go back to the previous page?
So we assume that P is real stable.
P is real stable now means this closed open business.
No. It's the original version of real stable. If all the xi's are strictly have a strictly positive imaginary part, then the polynomial is non-zero.
Yeah.
Okay. Now let's first look at just this Rx. So what is Rx? So these x2 to xn have positive imaginary part. X is just an indeterminate. So it's a univariate polynomial.
Yeah.
Can
This has no roots in the closed upper half plane, you're saying.
Yeah, because suppose it did.
Uh-huh.
So suppose that root was S. Then what can I say about this polynomial P S y1 to yn? It has to be real stable.
No. But x could have its imaginary part to be 0 though, right?
That's what I'm saying. So suppose, yeah, so let's just see. So it's the same limiting argument we've done many times now. So let's look at this polynomial. Suppose S is this root. Okay, so let's just do this. So here is Rx is equal to Px x2 to xn, where imaginary part of xi is positive, and xi.
Xi is real. X is real.
Yeah. So suppose there exists a real S such that Rs equal to 0, but then Ps x2 xn must be real stable.
What do you mean real?
So this what I mean. So this polynomial, but then this polynomial T y2 to yn given by P S y2 to yn must be real stable. But this is contradicted because.
Wait. Okay. So T y2 to y. Okay, y2 to yn are not indeterminates, is it?
Yeah, they're indeterminates.
Yeah, and P of S must be real stable. Why so?
Well, because we are so remember this, one of the slightly non-trivial things we did. So whenever you take a real stable polynomial and put one of the things to be real, it still remains real stable.
Okay.
Unless it just vanishes completely or something.
Okay. I see.
For the univariate statement, Piyush, why did we have all those conditions? I think it is true even if things vanish.
I mean, to avoid division by 0, like what is preventing the one?
There will never be division by 0, right? Because either it is the case that a constant is achieved or the all zeros polynomial is achieved, which you are.
So the argument, yeah, you can get rid of that, but the argument I did had 1 over Ri in it, where Ri is the root. So you have to just argue separately about the 0 roots.
Yeah, that's all. Okay.
Yeah. So that's just to avoid the boundary case. This is just the proof of the thing we did. So we can apply the univariate calculation we did earlier to get a contradiction. Get a contradiction to the assumption that the imaginary part of x1 is also the same. Okay, so the exercise is to make sure that all the boundary cases can be handled. So I haven't handled all of them above, and all the boundary cases where terms just identically vanish can be handled appropriately. But apart from that, what we have gotten then, that is, if P is x1 to xn, real stable, then the multi-affine part in x1 applied to P x1 to xn is also then you can just apply it apply to all the variables, right? One by one, and which implies that the multi-affine part. So this is basically all those terms in which every variable has degree at most one.
So this gives the multilinear part of it is always real stable, is it?
Yeah, affine because the constant term also survives.
Yeah. It's very nice.
Okay.
So, is there, Piyush, like an intuitive explanation? Like maybe in the univariate case, is it saying that because we are looking at the behavior of very small substitutions of x1, so only the linear part matters or something like
No,
that?
yes,
Like,
I think that it's the institution is more to do with just this fact. I mean, just this thing that the linear part basically captures the function. So like the linear part and the part together capture in some sense the sum of the roots. And yeah. So if you're in a sort of reasonable set, then you're like, I mean, basically, yeah, they capture information about, say, that like say the mean of the roots, right? Mean of 1 over the roots.
So for linear polynomials, isn't been real stable equivalent to that every sign is same? Or
No, because I'm just going to give you an example where it is not. I think. Yeah.
What was the question?
So his question was that isn't it the case that in every real stable polynomial that is multilinear, all the signs have to be the same.
Huh? Sorry.
All the signs have to be the same.
Which signs?
Like the signs of the coefficients. Yeah.
Huh? Sorry.
Signs of the coefficients.
Oh, signs of.
But that is not true. So and if I'm understanding,
I mean, the determinant was also an example, right?
it's not.
Yeah,
it's not a linear polynomial.
Yeah,
It
determinant
is
might not be.
multilinear.
No, it is not. It is not multilinear because you're multiplying each matrix by a yi. It was multilinear in the tree case, but it's not in general.
No, the spanning tree was a multilinear polynomial.
Yes, but general.
But in this case, we're talking about the affine part means linear in each of the variables.
Yeah.
Total degree is 1.
So we'll just see an example where that is. Right? So yeah. Yeah, I don't. That is.
Sorry, I meant sign of the imaginary part of the coefficients.
Oh yeah. But yeah. So right now we are almost always talking about polynomials which have real coefficients. So that is. Yeah, imaginary part I can completely imagine, and that probably is not hard also. But yeah, okay, I'm not sure how to do it. But we are always also doing it. We have real coefficients for now. So that's. Okay, so now what about the matching polynomial? Where do we? So now can someone guess what should we do about the matching polynomial? So assuming this multi-affine part. Okay.
What was the matching polynomial? Sorry.
So yeah, so this was the thing. So for so you have a variable for every vertex, and what you do is that your polynomial is that for every matching you have a product of the variables corresponding to vertices matched in M, and right, and you have -1 to the power M. So maybe let me give a
This is
Is it like the?
This is a multilinear polynomial, right?
This is a multilinear polynomial, yeah. And we want to prove that it is real stable.
Oh, so you want to express this as somehow as a non-multilinear polynomial and say the affine part of that is.
Yeah. So let me do something. So let's consider a polynomial px y, which is just 1 minus xy. Messing up something. Yeah, is this
But
Yeah,
this is also non-homogeneous, no? This polynomial.
Which one? Yeah, that is fine. Nothing we've done so far has been about homogeneity. But let's look at this polynomial, 1 minus xy.
yeah, this is real stable.
Yeah, and let's just check why. So the point is that if say so if I take a plus ib, c plus id, right, this is ac minus bd plus I times is AB. Sorry, I'm just blanking out a little bit. Yeah, okay, sorry, yeah, there's something much simpler. Sorry. So suppose, yeah, so the point
So the
that
sign of imaginary part
yeah,
of x and 1 by
if
x
pxy
always
equal
have
to 0
different
implies y equals 1 by x.
and they have different sign always.
Yeah, so
The imaginary
which,
part.
yeah, so y and x cannot both have positive imaginary part. Okay, now yeah, good. So we have a polynomial, this real stable polynomial. Now can you now with this hint can you so let's look at a polynomial. Let's look at this polynomial in the same set of variables that as the matching polynomial, which is I take a product over all the edges in the graph of
XU
1.
minus XU.
Yeah, 1 minus x dx. What is the multi-affine part of this? Well, first of all, is this real stable?
Product of real stable polynomials.
Yeah, so this is real stable, right? And what is the multi-affine part of it?
Multi-affine part means or the terms which have total degree 1. Right?
No, terms which have in which every
Has
variable has
individual
degree exactly less than equal to 1.
Right, so every matching will contribute minus 1 power size of m to the sum.
Yeah, every variable has.
Yes, right, sorry. I thought okay. No.
Okay. So okay, so
That's it, no?
yeah, that's it. Yeah.
I have a small doubt actually. I don't know if it's relevant or not. So can't you say from the so this 1 minus xy or product of 1 minus xi yi, whatever we are getting, it's giving me a surface of parabolas, right? Paraboloids and intersection of them.
Hyperboloids or whatever.
Yeah, hyperboloid and intersection of somehow from that we can.
But these are all in the complex, not in the real.
Okay.
But anyway, right? The thing is that the original polynomial we're interested in has nothing to do with it because it's doing well. It has something to do with it, but it's like a very strange operation that you're doing, which is not a very nice operation in terms of geometry. Right? It's you're just discarding some terms, you're discarding all the terms in which any variable has degree 2 or more.
Okay.
But we just saw that about enough information about roots already contained in that. Yeah.
This one could have been replaced with any real number.
Exactly. So you'll also get this for
terms.
you'll also get it for weighted matching polynomials.
Mm-hmm.
So exercise this that you can also get it for edge weighted matching polynomials. Any positive edge weights you'll get this. So Hellman and Leib actually work with positive equals also. And that's
No. So, but I'm sorry, but if you replace the 1, you mean the coefficient here could have been anything? That's what you mean. Right?
yeah. So I mean, you just put a WE here,
Right.
where W is positive. That's all.
No,
Then-
that's right. But I thought Siddharth's comment was this 1 minus, that 1 could also be replaced by something.
Yeah, but that is fine. It will just take that out. Like, I mean, these are two things are equivalent because you just like WE minus this is the same as
Okay.
1 minus 1.
Yeah. Sorry. Yeah.
Okay, so what is this good for? So let's just see something. So suppose I put all the variables. So if I put, so this means in particular that mu gx, which is summation minus 1 to the n, x to the size of the matching, 2 times.
What did you say already?
Sorry?
Minus 1 to the size of n? No, I mean, are you writing a new polynomial or?
No, yeah. So I'm just, what am I doing? Yeah, so I'm just saying that this.
You're plugging all variables
equal to x.
Yeah.
Or into the matching polynomial.
Yeah. Right.
But that would be just, I mean, that would be real rooted, no?
Yeah. But no, so this is not correct. So I have to add something here. What do I have to add?
A constant term.
No. Yeah. So for this is the number of matchings of size n. So let me call that Wn or something. I don't know what to call it. An.
But your sum is going over all matchings, so you will have to change.
Yeah. Okay. So yeah. So I don't want to do that. So what I want to write it is like this. So yeah. Okay. Maybe I will just minus 1 to the n, x to the p, n, which is the same thing as k goes from 0 to I don't know, n by 2, right? And you have minus 1 to the k, ak, x to 2k. Okay.
Size key, right?
Yeah. So and now from this and this thing that we've done about log concavity, etc., we can get results which say that the number of matchings, the sequence of how many matchings there are of a certain number of size is actually log concave. In particular, it's unimodal. So up to some point it increases and then it starts decreasing. So this is not obvious at all a priori.
So Piyush, can you please repeat what you just said?
So we showed earlier that coefficients of real-rooted polynomials have certain properties, right? That they have this log concavity, ultra log concavity, etc. properties. So using this and so right now there is this degree 2 here, but from this, so yes, when we'll do this next time. So we'll show that from this real rootedness, we'll get that the coefficients of the matching polynomial, which are just a number of matchings, have this log concavity property. In particular, that would imply that it is unimodal. And if you want to prove this without this, so commutarly, that's somewhat non-trivial task. You can do it. I think it was, as far as I know, it was first done in a paper by Jerem and Sinclair, the commutatorial thing. But I think that gets, first of all, a slightly weaker result, and it's not maybe as straightforward as just going through this process and then applying the generic thing there. coefficients are log concave. So we will do this in the next class. Okay, so maybe
that
in the
thing is just
remaining
substituting
minutes,
x
let's
square
just.
equal to y.
Sorry.
I'm just asking make that conclusion. You have to make x square as a new variable y.
Yeah. So something like that. So
Okay.
yeah. So I think that just goes through. I might have to change a little bit here.
Sorry, what's the
Yeah.
issue with having a 2 there?
No, so the thing is that right now there are like these zeros, right? So there is some like in the middle there are zeros in the code.
Oh, okay. Not
So you
all
have to get
coefficients are there. Okay.
Yeah. So
Okay. And that's not allowed, right?
yeah, I mean it's allowed, but that gives you something not so nice. It just says like it's something. It's giving you something not interesting because you remember that
It says 0 greater than equal to 0.
Yeah. So this can be fixed, and so but maybe today let's focus on the map operator and just. So in the proof that I did, the only thing that is possibly suspect, which you should check, is what happens. So basically, we had this notion of real stability where 0, like so okay. So in our case, it will not be a problem because things are not vanishing. But in general, to this map, you have to be careful about things vanishing. So you have to just argue that So if Q is not real stable, then it is not vanishing. So if Q is not identically vanishing, then one of A1, A0, something is not also identically vanishing. And so these things that we were doing here they're still going through properly. So if R is completely vanishing, then Q is also vanishing, something like that. So you just keep track of those kind of arguments. This is not be a problem when you're applying this map to the matching polynomial because coefficients are so nice, nothing is going away, nothing is vanishing. There's always a constant term which is always there, so it's taking care of things. But in a general setting, you have to be careful about making sure that those boundary cases are handled correctly. So what else? So we did other thing that we did was this matching. So this one was So here it was mostly commentary. So once you had the Matrixy theorem, after that the stability theory just direct to apply, and you got the result. So the negative association thing I'll probably put in a homework. So going from negative dependence to association.
Here, why does it negative association work for the matching polynomial? You could similarly set some y's to 0.
No, but now it's no more a probability distribution. There are negative coefficients.
Oh, okay. Yes.
Okay, and one thing you can also try to do as an exercise is that you have the matching polynomial when we have proved real rootedness for it. That should imply something, right, for this other polynomial also where there were no signs. So just maybe try to figure out what does it imply.
Sorry, say again.
So so here we said that this matching polynomial with this -1s etc. is real rooted. So, but there's another maybe more natural thing, right, where you ignore the signs.
Where you
ignore the signs, where there are no signs.
Okay.
And so.
In fact, what was the role of that sign in the whole argument?
So right. Actually, that's a good point. So maybe let's spend some time. So where did the sign come from? What would have been?
The product 1 minus
xy.
So if I would have put a 1 plus xy there. And what is the stable? So 1 plus xy is not stable with respect to the upper half plane, but it is stable with respect to the right half plane, for example. So you have right half plane stability. Okay. So you might still be able to do some of these things. So maybe one exercise to see how much of it can go through.
But from right half stability, you cannot conclude that it will have real roots, right?
So the thing is, so the question I will ask them is, does this map argument, does that work for the right
half stability?
But the conjugate root theorem will not apply here.
But where did we apply the conjugate root theorem?
So I mean
All
to
we-
show that real rooted, real stable polynomial, a real coefficient.
No, that was not needed because you just took that f prime 0 by f0, no, and then you got 1 over that thing. Yeah.
So now it's like, yeah, so some of so actually I haven't tried this out. I think some things will probably break, but many of the things should just go through because it's really just rotating the variables by I. So if it is homogeneous, for example, many things will just go. So yeah, if they're homogeneous, everything just goes through right away. Right? It's just the same multiple ones. But yeah, so it's good to sort of check what stability operators preserve what. So which stability things are preserved under what operations. So, yeah, here the thing that breaks is that 1 plus xy is not real stable, but it is right half unstable. Okay, so let's stop here.